Okay, thank you, Alba. Thank you, everybody, for coming back. So let me just briefly tell you what we were doing last towards the very end. So we need to get rid of the potentials to write the effective theory for the long distance effective theory that includes only the radiation modes. And we were talking about doing this, sorry, at the classical level, which meant the saddle point approximation, which means we're treating the Wavelengths as external sources. So it's the same that you do in field theory. So you have external source J, you compute a partition function. The only difference here is that the only diagrams that you will keep, it will be tree level. And since, as we were saying before, also we're looking for the effective action, which is this guy here. So it also exponentiates, as you know. For example, if you sum all the tree level disconnected diagrams, they exponentiate into the 1-point function. And this is the one that we're after, for example, if you were doing the order G, what is called the first Post-Minkowskian order. And I was telling you that the mass is just the integral of T00, which is very simple to see here from the multiple expansion that we talked about. But it's easier if you're computing the binding to match the one, so to speak. So we don't need to put external gravitons, external long wavelength gravitons. We can just match in vacuum, which is usually what you do also when you try to compute, say, the binding energy in QCD. And sometimes you do it in the computer because it's strongly coupled, but it's literally doing the same calculation. So there are no external gravitational waves here. We're just computing the vacuum by integrating out all these potential modes, that the binding modes, which are the optional modes that we discussed earlier, and we match into this wall line theory that is just the zero order without the H00 longitudinal, long wavelength field. So it's just the one, which is the mass, and the mass is energy, and the energy is kinetic plus potential, so we can read off the potential. And remember the potential, which is what we match, right? We integrate out and we match into the potential. And remember the potential is what's gonna give us the equations of motion that we need to input in the derivatives of the multiples that will give us the fluxes. And it's also the potential that allows us to compute the binding energy, kinetic plus potential, which is what we need from the conservative sector in this adiabatic expansion to compute the phase. We needed the conservative energy, we needed the flux. So this will serve two purposes. It will give us the conservative part of the energy, and it will also give us the equations of motion that we need to input in the flux, in the derivatives of the multiples, okay? So this is what we need to do systematically. You just have to crank. We know what the Lagrangian is. We know you have to do some background field gauge fixing as we discussed, but otherwise this is very simple. We have the Einstein-Hilbert action. We have the wall line theory that includes also the short distance physics that we discussed earlier. And we just do this integral, which means just sum a bunch of diagrams. We just want to exponentiate them to look at the effective action, and therefore we just get the connected guys. And this is one example. For example, this is 1, 2, 3, 4, 5, 6 loops. Okay, and this gives us the potential. And I was just telling you why, in principle, this integral, nobody told you about the potential modes or the radiation modes, etc. This is a separation of what we call the method of region, is that this integral, we have different regions where you have the full propagators of the H mu nu field. So why would I just keep these potential modes? Is because there is a contribution to that integral that comes from what we call the potential modes, which is the part that contributes to the real part of this effective action, which give us the binding, okay? And this we can see, and I was trying to motivate to you where these potentials come from. For example, with the 1-point function, because we saw that is a very easy calculation of the 1-point function. We were taking the coordinate time to do this calculation, and we were seeing in this case that if you go, ignore this for a second, because that's just the parameterization of the potentials, but if you go to the static case, in the same calculation, you have a full propagator. However, the integral in time, because the positions do not depend on time, basically makes this whole thing static. And this is exact. We haven't done any approximation whatsoever, except that there's a linear theory. And therefore, a linear order, we get just the Coulomb potential. Done. Now, obviously, when you start moving, you're not going to get rid of this P0 because these guys now are time dependent. So what we do is this expansion. So we expand the full propagator in this region, this potential region, by saying, okay, a leading order is the Coulomb interaction, but then we have corrections, which are deviations from instantaneity, which are these P0s, which you can trade by derivatives. And how do we do that? Well, so if you have this correction here, So the first leading term is here, as we just determined. It integrates, when these guys are static, it integrates to the delta. But now what we're gonna do is do the integration differently in different order. So here before, we were integrating here, as we saw here in the dt, right? Now we're gonna integrate in the P0. And what's gonna happen is because we neglect this piece, we expanded it, all the P0 went into the next term. So the integral of P0 just gives me delta of T1 minus T2, okay? So this recovers the same expression we had before. Now we have a correction. The correction of the P0s now are in the expansion of the propagator, is here. This again will give me a delta. The P0 I can trade by dt1, dt2, and then integrate by parts and hit this guy. And this brings velocities and p's. So what's gonna happen is you have another integral, which is very simple, which if you go here, it just means propagator, propagator, insertion. So here you have p squared, so you have two propagators, so you have p4, and then the p0 square insertion becomes pv. So it's literally now becomes pi pj over p to the 4, and you can easily do this integral, and then you get a correction to the Coulomb potential that it would be there also if you were doing electrodynamics, by the way. It will be linear and v instead of quadratic. And it's a correction that counts deviations from the fact that the propagation is not instantaneous. Okay, there is some time delay, and that is a correction of the potential that you can parameterize, and you can include this to all orders. You keep going. These integrals at some point they become tricky. One of the tricky things that you immediately realize is because we put p's downstairs, at some point we might run into infrared divergences, and in fact you do run into infrared divergences. This happens at 4 post-Newtonian order, and you have to understand what is happening. And what is happening is that there is an overlap with the region. The infrared is the long-distance radiation modes. So there is an overlap with the radiation modes that you need to subtract away. And if you subtract that, then everything is fine. There's a divergence in the radiation sector that cancels exactly that divergence in the potential. But otherwise, you're good to go. You keep cranking the machine. So you need to include higher order effects. Also in the couplings, the sources themselves, not just the propagation, but the source depends on the velocity. So you need more couplings of derivatives on the propagators from the p mu alpha beta that we have at the beginning. In some gauge, but obviously the answer will be gauge invariant. It's often convenient to use what is called the Donder or harmonic gauge, background harmonic gauge, or linearized harmonic gauge, depending on what calculation you're doing. This completes all the 1pn at leading order in G. But remember, because in post-Newtonian, this is not post-Minkowskian. This will finish post-Minkowskian. If we could resum all these guys, it will finish exactly the one post-Minkowskian order. But since we're doing post-Newtonian here, not post-Minkowskian, we need to include the G-square corrections because the G-square V0 effects are of the same order as the GV square. And that means we need G-square contributions. We need 2pm contributions to complete 2pn, sorry, the 1pn, 2pm to complete the 1pn potential. And therefore, because of this mixing, we need to include the nonlinearities. Well, where are the nonlinearities coming from? As we determined, there is an h² coupling from the square root, and there is an h³ coupling from the gravity. This gives you a very simple integral you can do by yourself. And I strongly encourage you to do this exercise because you guys by now should be able to do this very easily and then feel like you are like beating Einstein, Infeld, and Hoffman to compute the 1pm potential in a few lines. It won't take you more than half a page, okay? You need a 3 graviton vertex, and for my thesis, I actually did it by hand, but if you Mathematica now, it's not so good. Anyway, so now I wanted to tell a little bit about the state of the art, where we are, but since I might not have time to go to the radiation, which is the last part that we need. We need the flux to compute the phase. Let me come back to this state of the art at the end. And because I'm very bad with the computer or the iPad, I could not move back and forth, so I'm gonna move it manually and come back to this later. So let's go to the radiation problem, okay? So we have to do exactly the same thing I was telling you before. Before we match the vacuum to get the binding, we could have also matched 800 to get the binding. I mean, you can also do it that way, and it gives you the same answer. It's just that it's easier to match the vacuum. But if you match the 1-point function again into the binary by doing the same integral that we said before, the M gives me binding, but the QE will give me the Q. So that's the guy that we're after. We want to match the Q now. And remember that I told you that it's convenient to match the T mu because moments of the T mu is what's going to give us all these Qs. Q, I, J, K, L, whatever, all the quadrupole, octupole, 16, and so on. There is one caveat here. And the caveat is if you look at this coupling, when the radiation modes couple to the potential modes, there is one subtlety. The subtlety is that the radiation mode is a long wavelength mode. It wants to be V over R, the typical support for the momentum of the radiation mode. Whereas the potentials, excuse me, the potentials live in the binding, live in our UV theory, right, in the 1 over R. So because we are having conservation of momentum on the vertices, once you go into a vertex of a potential coupled to a radiation, the guy that comes out has Q plus K. In time is okay because as we said, the time does not decouple, but in space, this does not scale homogeneously, and this is bad for an effective field theory. So what do? Well, we do the same that we did with the P0 before. This propagator, the one that enters here, we're gonna expand it in K. And this is literally the Fourier transform version of the expansion in derivatives that I did at the beginning of the radiation field. If I expand in derivatives, this guy, the field in space is the same as this expansion in Fourier, okay? So all the K's go upstairs as in the multiple expansion, and then we can match directly to the multiple expansion. And let me show you how that works. For example, for the leading order quadruple. So what happened with the leading order quadruple? Remember that we did this moment relations when we did the matching, the generic matching with the T mu nu, and we found that the Qij is the integral of T00 at leading order in the derivative expansion, right? So now to match into this idea of the multiple expansion and the expansion in K that will end up being the same, we're gonna Fourier transform this T00 only in space. So this is the Fourier transform in space of the T00. So picked up the momentum, okay? But only in X, not in T. It goes for the right. So some partial Fourier transform, okay? So if we span this side in K, if we span the Fourier transform of the T00 in momentum, so at second order, we're gonna have two derivatives. We span this guy some coefficient of the expansion of the Fourier transform. And on this side, it's very clear what's happening. So this guy, the support of the K, this is the whole point. So the support of the K will be the external radiation. The support of X will be the R, the distance. So the expansion in KR is literally this derivative expansion in R over lambda. So expanding here will be the natural way to do the multiple expansion at this level. And therefore, if you bring two guys down, you immediately see that the second order expansion, when you factor out the K's, is an integral in X, because this is just integrating X, xij T00 kij. And that's exactly telling you that this coefficient of the second order expansion of this guy is precisely that moment. And this is true to all orders. To all orders in the multiple, but a linear order in derivatives, meaning if I keep adding x's here, xi, j, k, l, etc., and I keep going to higher orders, here this is this dl here is all these indices, then the T00 xi, xj, blah, 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 the leading order in derivatives multiple will be given precisely by that expansion, okay? Other moments will be the same. We're gonna need the Tij component or the T0i component and so on. So what do we need to do? We need to compute this guy, this 1-point function, match into this theory, right? By matching the T mu nus, by computing the T mu nu in Fourier space, but in partial Fourier space, only space-like Fourier space, expand in K, and pick up, say, the second order in K expansion of the T mu nu that comes out of here to read off, for example, our Qij. And that's how we're gonna do it. This is very easy. At other G0, this is literally trivial. In fact, you can just match the T mu nus by summing the two wall lines. So the full theory, the UV theory, is just two wall lines, right? So you have m d tau, there is velocity corrections that it has, the T mu nu has velocity corrections as we determined before, but this is a leading order in G, which means just mass. There is no binding here. So it's just the mass here. There are PN corrections, but remember, I'm not doing yet PN corrections. I'm doing this expansion, little r over lambda, which happens to be PN, but it's independent in principle, right? So there is a PN expansion of each one of these guys at a given order in derivatives. And then I have to keep everything that I need to the given PN order, okay? But in principle, they are independent. So remember, this just follows from the a leading order in G. This just follows from the MD tau, which this is flat. So this is the usual thing. This is nothing fancy going on. I was just emphasizing the same point that at each order in derivatives, each one of these t, you have to keep many Pn contributions, and this will be a leitmotif for us. So it's very easy to see here, if your Fourier transform this in space is e to the ikx, if you span to second order, what is the multiple? Do that as an exercise. That's why I didn't write it. Qij expanded to second order of just the delta, it gives you precisely that the Qij is mass xx. So the only thing is mass e to the ikx, the Fourier transform and the delta go into each other, right? So then the leading order will be just mxx. Do that as an exercise because it's straightforward, right? So this T mu matching in Fourier space expanded to second order that give us the Qij. The leading order is literally what you expect to be, okay? At 0 Pn order as well. Imagine also there will be higher order corrections. It will be just mxx, okay? There will be mb square also, and that mb square is gonna complete the binding energy. You're gonna have mb square, and you're also gonna have gm over r. So how do we get the gm over r? That will be the most interesting part of this calculation. And by the way, you can do electrodynamics this way, and this will be a beautiful exercise. You can entirely solve Jackson this way, and you don't have to do any of these linear potentials or whatever. This is basically straightforward. So what do we need to do the full 1 Pn correction? Well, we need to include this velocity effects, but we also need to include higher orders, both in the derivative expansion and higher orders in Pn. And here I separated what we need to do. We have to do the quadrupole at order v squared, which is the one that we just include these terms here. We also need the octupole at leading order, so order v0, and that's because the octupole, when you go, remember there's another derivative. The octupole is going to have one more derivative than the quadrupole, and that derivative is going to hit the x that's going to give you v. So when you include everything, you realize that the extra moment will give you also an extra power of v, and c squared gives you also a v squared. So that matching will come from this, as I told you earlier. So to really do the 1 Pn, we need the leading order octupole, which is just mxxx. So that one, the matching is trivial. Then we need the current as well, because the current, you remember, have the T0K, and the 0K, as you see here, from the leading order, we have a V in it. So that V will also contribute. So we also need the leading order current, because it will pick an extra V from the fact that the current is a velocity, obviously. So the only interesting calculation, the only one that will take us a little work, is the G correction to the quadrupole. Because when we do this matching, as I was telling you here, this matching here, there will be a binding that will radiate and match into our quadrupole. So I cannot use my fingers. Let me see. So there will be, ignore this for a second. It will be this binding here, this guy radiating from the binding energy itself. And that we need to calculate, because that will dress our quadrupole. Now, the nice thing is that if I hadn't done it this way, I wouldn't know how to include this effect. If I hadn't separated potential and radiations, they would be all mixed. I wouldn't even know at which order what enters. When I try to compute fluxes, the things that are square naturally without interference, I also wouldn't know how to separate it. That's the whole group theory calculation that we did earlier. So all that organized our calculation in steps, such that we know exactly what we need to calculate at which order. And that's very, very convenient, okay? So now let's go and check that calculation. This one here, which is the only one that is interesting. There are two aspects here. The first aspect is that we need to include the corrections that I told you earlier. So if you go into a second order in derivatives, in the multiple expansion, remember the first one was the Tij, that through the moment relations gave us T00 xixj. The first one, dkxk, gave us the current. Now the next one that has kxl, this here, I already told you that anticipated that if we decompose this object in irreducible representations, this is a 2, this is a 2, it will contain a 2, and this 2 will be an electric 2, and it will dress up the quadrupole. So there will be a correction in the derivative expansion to the quadrupole. It will no longer be T00xx. And these are the terms that appear. There is a trace that appears, and then there are derivatives of T00, and there is derivatives of T0k. So the quadrupole is no longer T00XX, it's T00 plus TLLXX plus this guy plus this guy, and some numbers in between. I think this one is 11/42, for example. We did a lot of moment relations to write it this way. It's very convenient to write it this way. Why is it convenient? Because now I need to Pn expand. And because I need to Pn expand these guys, it's easy to see that this guy starts at V0, but it will also receive V square corrections. This guy starts at V square, this guy starts at V square, and this guy starts at V square, without spin at least. And therefore, I know how to calculate now the Pn expansion of each one of them that I need to include at a given Pn order. So let me reiterate. In the derivative expansion, I need to keep more orders because R over lambda will cost me V, and I need that V. But each one of those T themselves are post-Newtonian expansions because they depend on velocity and because they depend on the other scale, Gm over R, which is also V. So you see all the scales are entangled, but there's a very clear separation of what comes from where, okay? So what we need is the correction to these guys, to the T00 and the trace, that starts now at G1. That's the part that we need. So this is the price to pay for correlated scales. That's exactly what I just said. So you need to keep track of what everything comes because the V's will come out from many different places. But we know what comes from where. I could have called these ratios differently, and I will know at which order I have to keep what, and then count in V at the end, okay? So the leading order was this. There is no binding here. It just comes from the deltas of the T mu nu that I just told you. The first interesting part will be this, the G correction to the multiples. And this is the guy that I was telling you. There is also a word line coupling, which is nonlinear. So this guy will also give me binding energy. And that one I also need to calculate. So this is the leading order radiation that I told you before. Is a stride forward, then to match the multiple is MXX. Is a stride forward to compute the flux too, because the dots I can just compute with Newton. So, and this you can do as an exercise, as an exercise in dimensional analysis, as a Fermi problem. Compute precisely that, the flux. Compute. You can also compute the amplitude. I haven't told you how to compute the amplitude, but it's very simple because it's the same that you will do in electromagnetism. In electromagnetism, you get the amplitude, the electric field, the A mu, as the dipole, right? So here, instead of being the dipole over R, it will be the quadrupole over R. And instead of being one derivative, you get two derivatives. So you can also calculate that, and the derivatives you can take with the acceleration. And then you can go ahead and check the LIGO data and try to extract from there a lot of information about the black holes. So just on dimensional analysis almost, once you know the structure of the answer. But that's why the shear mass center, which is the only thing you need to realize. So this is very interesting, very simple. And in fact, LIGO does this as well. They do the very simple leading order radiation to fit, for example, or a guess of the total mass of the system, which happened to be around 60, sorry, 65, I think. But then it comes the 1pn correction, and the 1pn correction will allow us to disentangle that shear mass that enters a leading order. There's a combination of masses that enters here, obviously. Just by this guy, I won't be able, with one observable, I won't be able to tell you what the masses are. I need to go to higher orders because that will disentangle. The combination that enters here is different than the combination that enters here, okay? So we need the G correction because the binding energy radiates. This is a new thing. This is a new thing for QED, and this is a new thing for QCD as well, because we don't radiate glue, at least not far away on shell as gravitational waves are. So this makes it a little bit more interesting that the calculation here includes the fluxes of the spin 2 field, okay? That serves as a asymptotic state of the theory, right? As our on shell asymptotic state of the theory. Very good. So now, as I was telling you before, we need both. We need the T00, but also the TLL, because at order G1, they both contribute at the same order. This is a G0, but a G1 that we need them, they will contribute at the same order. So for example, we need a diagram like this, and we're looking at both contributions, the 00 and the LL. We are matching the T minus, by the way. We're looking at this 1-point function, right? Whatever multiplies the H, right, is our T minus. And the calculation is easy. You just use your Feynman rules. There is a vertex here. This is the thing that I told you earlier. there is a radiation mode, sorry, a potential mode here that is shifted. There is a 3-graviton coupling here. There is this guy that has to do with the separation. When you compute the potentials at x1 and x2 will pick you this guy. And this guy is just from the radiation and the fact that these guys are localized. And then you will see that this eventually ends up in the localization of these bodies, okay? So this is just the calculation, it's very simple. We have to span this K, as I was telling you before, because this does not scale homogeneously, and we want to match into the multiple expansion. And what we do is also very simple. We do the completion of squares. You have seen maybe this trick many times. So this guy here, you can write it such that it kills this guy actually, and makes your life easier. And so you pick up this K upstairs, and this Q kills this Q. But then when you have the integral in Q, with just a K plus Q, you can just shift it. K plus Q goes to Q plus K goes to Q tilde, whatever. And that's very easy to do with. So do that as an exercise as well. It's a very simple integral to do. And then you can extend the 1-point function correction. And then you'll see when you end up with the integral here, that you get a correction that goes like Gm over R, which you expect. You expect to scale as Gm over R. And that gives you a correction that from the 0, 0, by the way, is exactly what you expect to be the binding energy, okay? So when you sum the two guys, you recover the binding energy, because that's exactly the same calculation that I told you before. But it's so much easier to match the vacuum than go ahead and do this calculation with C0, 0, because you have to do this expansion and so on. The vacuum is much faster, but you get the same answer. You are basically going back to get the binding energy, and this is the potential that we need in 1 and 2 that we need for the equations of motion, okay? So there will be a correction when you add these guys, and you also include the other contributions from TLL, the contributions from the dot, the contributions here, I forgot to write it, from 0, 0. All this will enter here, all this will contribute, okay? Actually, I wrote it here, recall M is the 0, 0. So there will be a correction to my Qij. There will be, when I expand to second order, right? And I read off the coefficients. When you start expanding this K, you start bringing the x's down, and those x's down are gonna be these x's here, okay? And the other thing is an integral in Q that will give me this potential. I mean, it doesn't get easier than that. You just expand in K and just write at each order, the moment that you need, we need to expand to second order. And then we get a correction to our quadrupole moment that includes some binding. And there are other effects as well. So it's not just the binding part, it's not just the 0, 0 part. There are other terms that came from the derivative expansion, okay? So now we can do the circular orbit case, which is often what we think happens. So there is maybe eccentricity at the beginning, but the eccentricity gets radiated away in gravitational waves. So we think that by the time that the majority, at least, of the binaries, by the time they enter the LIGO band, they have circularized. So most of the templates that we use are for circular orbits. And this is very nice because that means that R dot is 0. That means that these x's are basically cos of omega t, right? If we're looking at the leading order contribution, for example, there is an omega here. So these guys here are R, so you're gonna get a cos square, and then you're gonna realize that if you go to Fourier space, this is in time, but if you went to Fourier space, this Q has the delta of omega minus 2 omega orbit, and that's the 2 that I was telling you at the beginning, okay? It's just these 2, okay? There's no mystery. And then you do and crank all the multiples, take derivatives with equations of motion from the Einstein-Hoffman action, potential that I told you earlier, and you expand in this parameter x, or xw, omega that I call it here, which is gm orbital frequency 2/3. And if you go to Kepler, this is velocity. So this is just one way to rewrite the velocity expansion, but now in terms of the frequency, because the frequency is the one that we're gonna observe. So this parameter x is very convenient because it counts powers of v, of Pn, and is already a function of the orbital frequency, which is what we want, okay? And then you have this is the usual mu, m1, m2, the reduced mass over m. This nu is related to the mass ratio, so it's mu over m. And then you see there is a leading order effect that knows about the reduced mass, which you expect, because if you go to the Newtonian case in the two-body problem, it's just a one particle with mass mu, and that's what's gonna happen here. But there's gonna be corrections to the quadrupole, Pn corrections, right? we should know about the mass ratio. And we know, so it's basically this nu knows about the mass ratio. When you input this in the flux is where you get the shear mass. And then this degeneracy of the shear mass is broken by this factor of nu here, that I could have written as a function also of Q, the mass ratio. And there are terms which depend on R, terms that depend on B. You can go ahead and put the dots, do the whole calculation with the, I actually wrote what mu is down here, sorry. And nu as well. And then you can go ahead and put all those dots, use the equations of motion that we discussed before from the 1pn Einstein-Hoffman. I actually have no idea what this means. Take the dots in E dot using the conservative equation of motion. We need the current and octopole, remember, and then we get a correction to the 1pn flux compared to the leading order effect, okay? So this, as I was telling you, depends on the shear mass, this depends on the mass ratio, and that's how we break the genesis. If we get these to very high orders, including the x to the 5, then we are sensitive to the love number. That's how we're gonna probe the nature of those compact objects. If there was spin, I did not say this, but spin enters before. Spin enters. So there's an x cube. So there are effects due to spin before. Sorry, this in this counting. So x is so it's 1.5 p. So the x is v squared. So this will be like a fractional power. So this enters at 1.5 because the spin breaks the v goes to minus v symmetry. So you get s dot b terms. And you get also SS terms that enter at 2pm. So this is the first spin effect, and you can disentangle those and so on. But the effects of the quadrupole deformation that I told you before enters at 2pm. So the CES square term enters at 2pm. Okay. So these effects that we need to calculate so this will be an x 3/2, and this will be an x squared. So these effects that we need to include, for example, include the effects of the spin will matter earlier. The point is that if you have high rotation, the point is that how to disentangle now, as we did here. Here we allow to disentangle the shear mass from the mass ratio. The spin is one combination of the spins here, a different combination of the spins here. So you need higher orders also to disentangle the spin contributions. And then you start getting the love numbers later that you also enter a higher frequency. This will be higher frequency, higher post-Newtonian order that you also need to disentangle. So that's what we need, not only high precision, but also good data analysis, long wavelengths, and a lot of data to be able to really nail these properties. For example, do some statistical analysis. If this coefficient is 1 for black holes, it's also a very interesting question. If the love number is 0 for black holes, it's also a very interesting question. So this is essentially the main goal, to wrap up this guy, the E dot, and the E as high as possible, because all the physics of the compact objects is inside those parameters that we want to extract. Not just the masses and the spin, also these coefficients. These coefficients could know about dark matter, for example, through the tidal love number or through the spin. If the spins are not very large, because, for example, through superradiance, you spin down and create this cloud, then you will see this cloud through the love number more than the spin. But it all depends on whether you can spin up back up, because maybe you are near an accretion disk and then you absorb angular momentum, you spin back up. So there's a lot of astrophysics involved as well. So this is not entirely the end of the story. This is almost everything. I told you, we get the binding energy. We get the binding energy, we can compute the T00 and to get the binding energy, or we can compute the vacuum and we get the binding energy. And that is half what we need into the phase. You remember, if we go to the very beginning of what I was setting up our problem, what did I tell you? I told you that this is, I should be able to do this more efficiently. So, okay, next time, here. So here, what did I tell you? I tell you that we needed the binding energy, assuming that there is no flux. So we can do that in vacuum. No H 1-point function, we match the vacuum the same way you do in QCD, and you compute the binding potential. From the E to the W, we get the W, okay? And this is half the work, because that's what we need to take this derivative with respect to omega from the conservative sector to get the flux, to get the phase. Then we need the flux that I just told you. We could do the radiation reaction instantaneously, but we use this adiabatic expansion, and we get this as a bunch of multiples. This dEdt we compute as a bunch of multiples. We match those multiples through the one-point function. We first did this derivative expansion to organize the multiples as moments of t mu nu, and then we match the t mu nu through the one-point function at a given order in g Newton, and then at a given order in post-Newtonian in velocity, and then each g will also cost gm over r will cost to v squared, and that will wind up as a full post-Newtonian order. And all that is what goes in here, and that allows us to compute the phase up to some order. Now that's almost everything. There's just one caveat here. Well, there are two caveats. The first is like the first thing you will ask me, which is highly non-trivial, and I only appreciated this relatively recently, is that this is a series in post-Newtonian, this is a series in post-Newtonian. This is a ratio of two series. How do you truncate it at a given post-Newtonian order? And how do you compute this? Do you integrate it in time, as I did it at the beginning? Or you integrate it in frequency, as I did it here? And when you truncate, you have to be careful when you also do Fourier transforms. So there are different ways to do these templates. And then there are called Taylor T4, for example. If you do it in time up to a certain order, you Taylor expand the full fraction, or in frequency, I forgot how they're called. So this is non-trivial, because we are truncating each one of these guys in PN, but we want to compute the phase, okay? So there's one extra subtlety here. But there's another subtlety, which is, I find, the most beautiful subtlety of all, which I haven't told you anything about yet, which is the following: that if we really want to finish this calculation, we have to also take into account the fact that the binary itself that is radiating is producing itself what you can call a long potential. The M that gives you the H00 coupling does not radiate. It matches into the Schwarzschild solution of the whole binary, or actually Kerr, because it has angular momentum. So there is a natural coupling of that radiation to the environment, to this long potential. And this is what is so-called tail effect. The tail effect is the scattering of the radiation off of the geometry of the binary. And this gives me logarithms. This gives me logarithms, and this gives me corrections to the fluxes and the binding energy. In fact, in the binding energy, it doesn't give me a log, because this log will be in the real part. In the binding, there will be a log of x at some point. In fact, it enters at 4 p.m. But there will be also a 1.5 correction here due to the tail. So there will be here an x to the 3/2, a 4 pi x to the 3. They are pi's, so that's what's going to come, give me factors of pi in the fluxes and logarithms in the binding. How does it give me a logarithm in the binding? Well, if this is related to the fact that there is a running for these coefficients, for the masses and the q's. And it's very natural to understand where it comes from. It's associated because these are long tails. So these things will give me infrared divergences, for example. But when you compute this in the binding, the type of diagram that we have to calculate is something like this. So it's the radiation back reacting on the object, on the binary itself, right? So this is the Schwarzschild source. This is the Q. This is the same diagram that I told you before. If I ignore this part here, this is the radiation now, but now it's back reacting on the geometry, on the binary, sorry. In our effective theory, I can do this calculation. This is the tail effect on back reacting on the binary as a radiation reaction force. Now you're gonna ask me, well, what about boundary conditions? What about in versus in out? So there's a subtlety there. You have to do in and not in out. But if you just look at the conservative part of this tail, in and in out are basically the same up to a factor of 2. So you could also use Feynman and get the right answer. Okay, just close this parenthesis. But the thing is that this infrared divergence that appears here, because it's a long time effect, when you basically put it back on the wall line, it becomes a UV divergence. This becomes a UV, and this happens in effective theory all the time. There is something that wants to be IR, wants to be a long distance effect. And in fact, from the point of view of the potentials, sorry, this expansion in 1 over P, vector P, is precisely given as the log of R, the IR divergence from the potentials that is responsible, that is basically the counterpart of this infrared divergence here. So when this guy becomes UV, this UV pole from the tail will cancel the IR pole that we get from the potentials. But it just became, this log of R, it just became a UV divergence because we basically send R to 0, the little r. And therefore that guy that wants to be an IR, it became a UV. And this happens all the time in field theory, in effective field theory. You have a logarithm of a mass. And that when you take mass to 0, or a very small mass if you want, that would be a logarithm log of m if you want. But if you take that m to infinity because you are integrating out of your theory, you transform that log of m, which wants to be IR, into a UV. So it becomes a divergent contribution now that you can actually give you logarithms that you can resum. So you can essentially use effective field theory to resum those log of m's, which in this case are log of b's, by mimicking as a divergence, as a UV divergence, and writing an RG flow for it. And this is what we did. And this you can do and get all the logarithms of V resum, the tail contributions to the energy and also to the flux, which I don't have time to explain. I just want to tell you here that there is something similar to a lamp shift because there is a correction to the binding energy, which is identical to the lamp shift. This is the lamp shift, by the way, this here. The difference with the lamp shift, and let me use another color. The difference with the lamp shift is that it's this integral without this guy, right? That's the soft photon on the background of the hydrogen atom, right? And when you integrate out that soft photon, you get the beta logarithm. You also get IR and UV divergences, and this confused even Feynman, who got it wrong, right? And then people understood how to do this correctly. In fact, what was his name? French and Weisskopf. And then Feynman corrected himself in one of his papers in a footnote 13, I think, where he admitted, maybe for the unique time, that he made a mistake when he computed the lamp shift, okay? So it's subtle because of these issues. And the same happens in the lamp shift, this cancellation of IR and UV. I had to mention it because it's super nice, and even wrote a paper about it that you can Google and find in the archive. But the same happens here. So the same kind of physics. The non-linearity is not because of the fermion line or the propagator in the case of the atom. Here is the long distance gravitational field interacting with the potential. So this is the non-linearity here comes from here. But it's a very similar integral. So as we know, also, as I was telling you at the beginning, we get a flux also from the cuts of those guys. And then you can easily power count this because the leading order flux is V to the 5. The tail is a V cube effect, as I was telling you. So that's where the VA comes from. That's where the 4PN logarithm comes from. That's a 4PN logarithm, and it gets like this. And this is now something very nice because recent developments in the theory of scattering amplitudes are precisely reaching a level of precision in which we are sensitive to this logarithm. And these developments in scattering amplitudes means do a post-Minkowskian expansion, do just expansion in G, and try to resum all the velocity corrections, but I'm giving over in G. Obviously, I'm not getting the exact post-Newtonian order because I'm just cutting in G at a given PM, post-Minkowskian order, and resumming in B. It's useful, but it's half the work. And now you see here, because these derivatives include accelerations, so this guy here will give me something like this, that will be proportional to G squared. Here, between those two, you get a G4 log of B. And this G4, which is a 4 PM order, is something that very recently people have looked at least from the point of view of the potential modes. They have found this contribution. The radiations are what gives the log of V. So in the potential, this becomes a log of R. In the radiation, it becomes a log of omega plus log of R, log of omega R is log of V. Okay, that's how we split this log of V that we can see from the long distance theory as an RG flow. Okay, I know these words might be a bit too much. I just want to tell you that there's a lot of very cool field theory here that is these days people are looking at, and we are looking at also from the point of view of the post-Minkowskian expansion. So to wrap up in the last 10 minutes, let me tell you a little bit more about that. What are we doing and what is the state of the art? I won't do justice to this, but I'll be happy to answer more questions if you guys have any. So I was telling you about the potential. So we separate the calculation in potential and fluxes. The potential calculation is easy, right? You just run into a bunch of integrals. So you have to organize your calculation properly And then you will see that you have a bunch of diagrams like this. There is internal momentum that we integrate. These are n loop in the sense that they are integrals. And the reason we're integrating here is, again, is because it's a point-like approximation. There will be a cutoff in momentum if we actually had an object, a body, but we're sending the body to a point, and therefore the integral momentum now goes into as high energy as you want. Therefore, this resembles the same as you will do in field theory with point-like objects. So you have essentially iterated green functions of localized sources that resemble loop integrals in field theory, okay? So they're like n-loop massless integrals. They're in 3 dimensions, right? Because we don't have the time part. The K0s are all expanded and traded by derivatives, and then you can do IVP reductions and master integrals, etc., and you can reduce it to integrals like this. So there's a lot of K's inside the integrals. There's a Q floating around inside. I just put it here, but it's everywhere, depending on how you do the master integrals, which is the last one that does the Fourier transform. That's the transfer momentum. You can even look at this because this is the only external momentum inputted in the diagram. It is like a self-energy. It's like a 2-point function with Q in and out with some bubble of massless 3-dimensional integrals, okay? So people do this for a living. In fact, Pier Paolo Mastrolia, who has done a lot of calculations with these integrals, he has found many, for example, of the 4-loop master integrals that were needed for the 4PN calculation, which, by the way, all of them also gave us the 5PN calculation recently. And the reason why the 4PN master integrals are enough for 5PN is because of the PN expansion and the way that this K0 couples and the way that these vertices also count powers of velocity. That's a subtlety. But the nice thing is that the 4PN master integrals gave us the 5PN for free. And so you just have to go ahead and calculate these integrals. You just plug it in here and do a Fourier transform and you're done. It doesn't get easier than that. Well, easier said than done in the sense that you have to go ahead and do the integrals, but that's all you have to do, right? So this has been done, as I said, up to 4 loops. That is enough for the 5PN potential. And even at G to the 4, there are even results like 6PN as well, when you expand the K0s, for example. So we have a lot of post-Newtonian data and overlap with post-Minkowskian data. I have this caveat here that I already told you. This is not the whole story. There is also the radiation reaction part that contributes to the conservative sector, like the lamp shift. You need to include it because, as I said, this could introduce divergences, and at 4PN, this becomes infrared divergent. The infrared divergent cancels with the UV divergence that I told you from the effective theory, where we collapse the binary to a point, so that log of little r that wanted to be an IR became a UV. And this is very interesting and very important to include the full calculation for the binding energy. You need to include both the tails and the potentials to the full answer, okay? But this is something where people can really contribute and really help, right? Because these integrals are hard. And as if you keep going and trying to understand post-Newtonian dynamics, we have to do the integrals and understand. For example, I think Pier Paolo, some of these masters had to do numerically and do an answer that could be matched numerically. And in fact, actually the PN, the GR people realized that in coordinate space, there is something called the First, the same guy for the contractions, a trick that allows us to actually do this 4-loop integral in coordinate space that Pier Paolo did numerically. So that was very interesting. That was one of the first examples, or perhaps the only example I saw that doing an integral in coordinate space is better than momentum. But in any case, this was very complicated integral. And then you see that people who are experts in doing the integrals are very, very useful. And in fact, the 5PN was recently solved in potentials by Johannes Blumlein, Peter Marquardt, Andreas Maya, who are experts in doing these integrals, right? So you see how QCD people, once they learn how we set up the effective theory, they can contribute right away. But now I stopped doing this. I mean, I still do it, but I started getting more excited about more recent, more modern developments, which is this whole idea of doing scattering amplitudes. Some of you might have heard about this. If you take a 2-to-2 scattering amplitude, anything that is happening here, in fact, right now, the whole on-shell philosophy goes in the direction that we might not need Feynman. You have to keep that in mind, that it's true that we might not need Feynman, but Feynman is still useful, as we will see. So you might have a way to compute this. double copy, generalized unitarity, however you want. Then you take the large mass limit, because we want these guys not to fluctuate. We don't want quantum fluctuations of this massive line. So we take the very large mass limit, which is what you will do in the heavy quark effective theory. You go to the very large mass limit, and then you go to the large impact parameter limit, right? Because you want these guys to be far away so you don't get contribution for pet creation or whatever. So which means you go to the classical limit of very large angular momentum, right? In that limit, you can match the 2-to-2 scattering to a theory in which you say, oh, it's a local potential interaction in momentum space. This Q is the momentum space. And then in that theory, this is, by the way, this is the Born approximation. If you do the 3-level, we know how to extract the potential because we do quantum mechanics. We do a standard quantum, this is a standard quantum mechanics. We match a standard quantum mechanics Schrödinger interaction into the 3-level Born approximation, and then we get this V. These loops are just the iterations in that expansion when you try to solve for the potential in the standard quantum mechanics, getting the amplitude of the scattering in the full field theory matched to the calculation in the standard quantum mechanics. These loops are just the so-called iterations, like Born iterations. But it's a very nice and compact way to do it as a matching in an effective theory, which was the work by Cliff Chun, Michael Solon, and Ira Rothstein, that they realized that they could do this. And they match, and then they get this V of Q, you do a Fourier transform, and they give VOR, and that was one way to get the potential. And the nice thing is that this is fully relativistic, special relativistic. So by doing a 2-loop calculation in G Newton, you can naturally include all the velocity corrections. So that's really nice, because that goes to G cubed, because 3 levels G, so 2 loops is G cubed, so you get the G cubed to all orders in velocity. And this was a breakthrough because it gave us for the first time one way to see what the resummation of some of those terms will be. But what we realized was that this computing potential, it goes very much against this on-shell philosophy of getting observables here, like an amplitude, or a gauge-independent object. It's not quite observable, but let's say gauge-independent object, into a gauge-independent observable without having to go through this matching of the potential. In fact, there's a lot of subtleties here because this guy is also infrared divergent. This guy has also divergences, but when you match, they cancel. And these divergences have to do with what they call super classical things, contributions, because you have the e to the I s over h bar. And when you expand, you're gonna get h bars downstairs, right? And some of those guys, like the box diagram actually, it goes like 1 over h bars downstairs. So it's like it's more than classical, it's super classic, but it's infrared divergent and it's canceling from both terms. So it's actually subtle how to calculate the classical limit and extract the classical potential, okay? So all that I did not like. So how can you do this much more efficiently? Well, we realized that there is a natural way to map the scattering problem to bound observables directly through the scattering angle. And then we also realized that you can do it, this is independent, but you can also get the amplitude and go directly to the angle through something that I like to call the impetus formula. Forget about what I'm saying if you haven't read the papers where we introduced this boundary to bound dictionary. But what I mean is that if I know the amplitude, I can construct the angle. But this dictionary that we worked out, we found that however you compute the angle, be the amplitude or something else, if I know the angle, I know all the observables of the binary case. And the angle naturally lives in post-Minkowskian. The angle is an expansion in gm over little b, or in gm over the angular momentum, but this includes all order in velocity. This is not cut at any Pn order. This does not want to be Pn. Whereas this is Pn because now the orders of G and V are mixed, as I told you earlier, because of the bound condition. However, I can sum all those velocity corrections that are given PM order by doing this map through the scattering angle. And this is one of the most beautiful formulas I think you're ever going to see, which is the scattering angle you analytically continue in the orbital angular momentum and in the binding energy to negative values of the binding energy and to negative values of the angular momentum, and you get the periastrum advance. It doesn't get prettier than this. You give me the scattering angle and I tell you what the periastrum advance is just by doing it.
Sorry, is this general? Like
Completely
for any
general.
force? Is this for any force or just gravity?
Absolutely general. Wait, there's one caveat, which I have not done spin. If you put the spins aligned, and therefore you remain in the plane. This goes exactly the same way, but J is no longer the orbital angular momentum, it's the total angular momentum. You have to flip both. You have to flip the spin as well. And this goes. But this now means something amazing. The periastrum advance descend from an object that some of you might know is called the radial action, because a derivative of that object gives me the periastrum advance, which is an integral of the radial momentum between the r minus and the r plus of the orbit, the two zeros of the radial momentum, okay? This is what Sommerfeld did to quantize the hydrogen atom, okay? This is nothing fancy. So this is the integral of the radial momentum with this r minus and r plus. The angle also has a radial action, which is an integral between r mean, the closest approach, and infinity. Well, we found a way to relate those two radial actions, to find a way to relate the r mean to the r minus and the r plus. And because the derivative of the radial action here is this guy, and the derivative is this guy, we could find this relation between these two. And this is completely generic. It doesn't matter what the radial momentum is as a function of the energy, which will depend on the Hamiltonian, but I don't want to go through the Hamiltonian, and I can literally get this. And if I get the radial action through the periastrum, which I get through the angle, I get all the observables. All the observables of a binary system I can compute through the scattering angle. Everything follows from the scattering angle. If you give me the amplitude, I can get the angle and do all the observables, and I don't need to do this. But we realize also that why do I need to do the amplitude? I can just redo everything that I just told you about the effective theory. I can reconstruct the exact same effective theory, but for the post-Minkowskian expansion, to compute the scattering angle and no longer to compute the binding energy and the flux and the Qs and so on. I can reconstruct everything, and this will be the next time I come to lecture maybe, how to get an effective theory for the post-Minkowskian approximation now to compute the scattering angle, from which you get everything now, everything resum in velocity. And this we recently introduced and computed and reached the same level of precision as the amplitudes at 2 loops, except for the very recent calculation by Svi and collaborators of the 3 loop. Unfortunately, they did not do the full 3 loops that includes the tail. We are now including the tails, and hopefully we'll have the full 3 loops calculation, including the tails. And let me tell you, to wrap up.
Actually, there is a question by Sasha in the chat.
Can you wait, Sasha?
Yeah, probably you can wait.
Okay, good. Let me just finish, and then you ask the question. Because let me tell you what happens with the integrals. It's always about the integrals. It's the integral stupid, like they would do about the economy, right? So the integrals that they get in the amplitudes to compute either the potential or the angle or to go through our map or so on, these are massive lines. And then you take the large mass limit, right? These guys are full propagators with massive lines. These are very difficult integrals. Massive. Of course, you're going to take the classical limit. It's going to simplify your life. You're going to realize also when you do the double copy and the generalized unitarity that you can glue things that already don't have loops. So there's a lot of simplifications. The full thing will be a mess, the full quantum thing. But yet, the integrals that they start with are not necessarily trivial from the point of view of the effective field theories. Why? Because we, even in the effective theory that I haven't introduced to you, but it will resemble exactly the same calculations that I mentioned earlier, we have external sources. For us, these wall lines that will scatter and give you an angle will be described as some x of tau, some wall line. So there won't be any propagating degree of freedom here, unlike what happens here. This is what gives you the infrared divergences that we don't have. We do not run into any infrared divergence. We don't need to isolate the infrared finite piece as you have to do here. These will be full propagators now, because we want to keep the full relativistic things. But as I said, there are external sources. There's only one caveat, which is when we compute the deflection, we do it iteratively. We look at the unperturbed solution. We found the kick. We input this kick in the lower order deflection, and we compute the correction from the lower order kick into the lower order deflection to compute the second order deflection, and so on. And this is what I call iteration, which means I need to know the kicks perturbatively and plug it back. That means that we're gonna get linear propagators from finding solutions of lower order equations, time dependent, because this is just omega plus I epsilon that comes from the x double dot force equal blah, right? So that we will get linear propagators the same way that you get in the classical limiting heavy quark effective theory, the same way that they get this linear propagator from the large mass limit. For us, it's an iteration of classical equations of motion. So it's a little bit simpler. But at the end of the day, what happens is that we end up with integrals. We look very similar to the, I didn't write them, but very similar to the integral that I wrote before. But instead of being three-dimensional massless, it's four-dimensional massless and have linear propagators. So we need to do a lot of IVPs, a lot of reduction to master integrals. And more recently, we have realized, and also something that Michael Ruf, Julio Parra Martinez, and Mao Sen also realized in the context of supergravity, and we translated to this case, that you can use differential equations to solve these integrals. And the potential and radiation contributions comes from the boundary conditions. And this is how we solved the third post-Minkowskian order. And this is how we're going to solve the fourth post-Minkowskian order. However, these differential equations fail to go into what is called canonical form when these integrals have elliptic functions, and it looks like the tree loop has some elliptic functions. And therefore, they were not able to get the radiation boundary condition because they had to span in potentials. So they only did potential, the same way that we do in our effective theory. But we seem to have better control, and we might be able to solve these differential equations, even though we will not go to canonical form, and naturally include the full potential and radiation conservative part and get the full answer at the four post-Minkowskian order. And this is, stay tuned, and this is beautiful because it mixes a lot of concepts from the theory of amplitudes, from scattering, connection to binary systems, to binary orbits, analytic continuations, differential equations, and loop integrals, the same way that you do with high precision calculations in the Large Hadron Collider, etc. That is maybe why my ERC grant is called LHC to Lisa, because literally that's what we're doing. And so this is very exciting. There's lots of people that are working on this. I'll be very happy to answer any questions or get any student interested on this, because I get students working now on this all the time. So I should probably stop here, and thank you very much for you guys for listening and holding up. Thank you.
So thank you very much for the beautiful set of lecture. I have a question, but maybe other people can. Sasha, do you want to ask your question, maybe?
Yeah, I had a very naive question. You had this formula in a box, the most beautiful formula. So my question is, what if you make if you consider minus on the right-hand side, that would correspond to something nice on the binary side?
Wait a second. Here?
Yeah.
If this was a minus?
Yeah.
Good question. There is one formula that I did not write that follows from here. It's equivalent to this one that has a minus. And it relates the flux of radiation between here, this problem, and this problem. If you're looking at the flux, then the formula of the flux of this problem and the flux of this problem, sorry, the other way, the flux of this problem and the flux of this problem will be related to a minus sign. Okay. So the fluxes will be related by a minus sign. Okay. So there is a nice formula for it, but it has to do with the invariance of J, because you see, if you put a plus here, this becomes J minus J invariant, which is what you want for the constant. If you put a minus, it has to be a flux. And lo and behold, you can show that the fluxes are related by the minus.
Okay, thanks.
Thank you. Are there any other questions?
Can I also ask one? So about this formula?
Yes.
So this reminds me a little bit of like a Regge theory, or like a more basic stuff like a poles of S matrix corresponds to the bound state. Is there any like a QFT derivation of this formula?
That's a great question. I started looking into that because analytic continuations of the Risam iconal, right? The gamma, right? The gamma function, right? Gamma of S and so on. When you analytically continue, you can get the poles of the bound case for the hydrogen atom, but you need to resum the whole thing. So it's a little bit non-trivial to see this continuation that works at any order in post-Minkowskian from the point of view of analytically continued the poles.
I see.
So it should work. It's just, it's a much harder to see it. But it was part of my motivation to find this, the fact that that analytic continuation existed. So that was a very strong motivation to look for analytic continuation between these two guys. And in fact, Julio Parra Martinez was also looking into this. I don't know if he ever reached any conclusion. And that's why the most recent work by Spee and Julio as well and collaborators, they are now going this way, to try to match directly what I said the radial action was and do analytic continuations, because this completely bypasses the Hamiltonian and goes directly to the observable. So yes, this is a very good question. There is more to be understood here. What my problem is that I did that for the hydrogen atom. In fact, this is also what they did in the 70s, I think. This guy Saint-Justine and so on. And in fact, Thibaut Damour claims that was his inspiration for the EOB. But you go beyond linearized theory, and I have no idea how to do anything anymore. I don't know how to resum it, right? Whereas here I can do to any post-Minkowskian order this analytic continuation, and it works. So I wouldn't know how to do the poles in the other case. But this brings me to another question. We can talk offline, because this should also work in supergravity. This should also work for strings, and this should also have a mapping in the CFT.
Yeah, indeed.
And this is what I told Joao Penedones already, and I'm trying to get him to think about it.
I see. Okay, thanks.
Yeah, so maybe we can just, is there any other urgent question? Because we are a little bit, otherwise we can always ask a question on the.
Yes, I put the lectures on the Slack.
Yes, on the Slack.
And please, I haven't gotten any question. I don't know if that's because this is trivia, too complicated, or uninteresting. So please ask. I mean, there are no stupid questions, okay? So as you can see, I mean, as you progress in the field, people will ask questions. So don't feel afraid of doing it.
Okay, so let's thank Rafael again. And
thank you guys. Thanks for the invitation.
Thank you very much. And thank you very much for the beautiful set of lecture.
Thank you.